we'll get into it straight away. These sequential logic is not a easy thing to do within 1 hour. It takes a while, right? And remember, we are trying to explain to you the little steps along the way and so forth. All right, so we were looking at a problem. We were looking at a problem, and the problem involved from page 12 of your notes. So let's, for those of you who haven't printed out the notes, I'll just quickly log into our Moodle shell. Hey, what the fuck's wrong with you? What's wrong? Okay, in the meantime, what I've done is, if I could have your attention, guys, I've placed the 2018 paper here, 2018 final exam paper, and my suggestion is, to start having a look and start attempting that paper. This year's paper is very, very similar, not the same questions, but similar, meaning, for example, question 1, you have this, and we'll solve this, I think. Yeah, we'll solve this today. We'll solve this problem today, or maybe on Wednesday. We'll solve this problem. Will we solve it? Let me have a look. All right, something slightly different, but anyway. So basically, the questions may remain the same, but the circuit will definitely be brand new. The circuit will be brand new. Same thing here, brand new circuit, and so forth, brand new sequence. So you need to get into it, and if you look at it, it's about 60 marks worth of questions from sequential logic, and if you look at it from week 8, so it's around about 100 marks is from week 8 onwards, right? But you still need to know Carnot maps, because you'll see sequential systems needs Carnot maps. Anyway, let's come back to the most important page of your 2018 paper, which is the appendix. So that's online right now. So if ever you want to have a look at the tables, the characteristic table, the excitation table, the state diagram, it's all there. All right. Now, we were looking at a particular note, and I think it is page number 12. There we go, page 12. We were looking at this one, right? Remember from last week, Thursday. So we deduced what D1 is, D2 is, Z is, right? So those are, so step number 1, once again, you're given a circuit. There's two things that you can do. Firstly, there's two types of problems, sorry. There's two types of problem. The first type of problem is that you are given a circuit. You are given a circuit, and you are required to find the state diagram, right? So you're required to do the analysis. The circuit is given, and you must do the analysis. Right? So that's like what we've got over here. Okay? You do the analysis, in order to find what is called the state diagram. State diagram looks something like this. We want to end up with something which looks like, where did it go? Here. That's a state diagram. All right? And I'll teach you what a state diagram is. So the way I'm teaching is, I'm teaching you the theory as we go along with the particular example type problem. All right. Now, the other type of problem is, of course, the other type of problem is the state diagram is given, or the sequence is given, and you're required to draw the circuit, go backwards. So that's a design problem. So if you're given a circuit and you're asked to come up with a state diagram, that's an analysis problem. Analysis means you want to find the behavior of that circuit. When you analyze the circuit, you want to know, hey, if the input is so many volts, what is the output? Or if your input is sinusoidal, what is the gain and so forth? What is the output? That's analysis, right? You are given a circuit, you're required to find out what the output will be. That's analysis. So in analysis, your answer is usually two things. Something called the state table and the state diagram. We're going to do that shortly. Secondly, the other way around, the behavior is already given to you. Hey, I want you to build a counter which will behave in this particular manner, right? Therefore, you will go backwards, you'll use the design process and end up with the circuit, all right? When you say design, that means you come up with a circuit. When you say analysis, that means you come up with the state diagram, right? This week's lab is on analysis, all right? Okay, now, the first step is we have to find the equations. This 4-step process. The first step is we have to find the equations. The equations to what? The equations for the inputs of the flip-flops. Now, the other thing I want you to note, how many flip-flops here? There's 2 flip-flops, right? How many bits does each flip-flop store? One flip-flop stores how many bits? 1 bit. Therefore, this is a 2-bit system. This system as a whole handles 2 bits. So, we have built over here, this circuit is a counter circuit. When we say counter in your normal think of primary school counting means to count 1, 2, 3, 4, 5 in a particular order. When you design circuits, your counter, somebody can ask you to count in odd numbers. So 1, 3, 5, 7, 9. So let's say if you had 4 flip-flops, your counter would have, if let's say somebody said, hey, I want you to build a counter. This is a design problem. I want you to build a counter. Counts in odd numbers. 1, 3, 5, 7, 9, 11. So how many flip-flops would you need? 1, 3, 5, 7, 11, 1, 3, 5, 7, 9, 11, and then back to 1. How many flip-flops would you need? Okay, so the largest number is 11 in your sequence. 11 means how many bits? 4 bits. You need 4 bits. 4 bits means you need 4 flip-flops. So your counter, what it means is you build a circuit with 4 flip-flops. In that case, 1, 5, 7, 9, 11. You build a circuit with 4 flip-flops. Can be any type of flip-flop you want, right? Sometimes the question will say, use a SR flip-flop. Sometimes the question will say, use a JK flip-flop or use a T flip-flop, right? Then, the first count flip-flop, the most significant flip-flop will have store bit 0. Second flip-flop will store bit 0. Third flip-flop will store bit 0. The least significant flip-flop will store 1. So what 0, 0, 0, 1 is 1. Okay, let's move to the next. Next clock pulse. On the next pulse. Next clock pulse, the flip-flops will flip. Yeah? Okay, flip-flops will flip. So the first flip-flop will have 0, most significant. Second flip-flop will have 0. Third flip-flop will have 1, and least significant will have 1, store 1. So each flip-flop stores 1 bit. So 0, 0, 1, 1. So that's a 3. Let's move on to when it's 1, 3, 5, 7, 9. So when it reaches 9, after 4 clock pulses, the first clock pulse, it gives you 1. Second clock pulse, it gives you 3. Third clock pulse, it gives you 5. Fourth clock pulse, it gives you 7. Fifth clock pulse, 1, 2, 3, 4, 5. So somebody press the button. 1, that's a clock. 2, 3, 4, 5. It should show 9. So first flip-flop will have 1. Second flip-flop will have 0. Third flip-flop will have 0. Least significant flip-flop will have 1. 1, 0, 0, 1. Then again somebody presses the clock button. So when somebody presses the clock button, those flip-flops will reset. Yeah, not reset in the technical term. They will change state. That's the proper term. They will change state. So sixth clock pulse, it's supposed to have 11. 11 is what? 1, 0, 1, 1, right? 11 is 1, 0, 1, 1. So first flip-flop will be of 1. Second flip-flop, most significant flip-flop will have 1. Second flip-flop will have 0. Third flip-flop will have 1. Least significant flip-flop will have 1. 1, 0, 1, 1. 11. Then somebody presses the clock button again. It's supposed to loop back. Remember I said that was the design of the problem, right? supposed to live back to 0, 0, 0, 1. So that's what we are trying to do. We've got two flip-flops here. What I just described with the odd number problem was a design problem. This here is an analysis problem. We want to know, after each clock pulse, after somebody presses the clock button or some square pulse come into the clock line, what does it show? Then what does it show? Then what does it show? Then what does it show? Because after every clock pulse, the flip-flops changes state. All right? Okay. Let's have a look at this. So first step was to, for you, if you look at the bottom over here, was to find the inputs, if you remember from Thursday's lecture, was to find the inputs into the two flip-flops. Right? The equations. The equations. Right? We also find the equation for the output. The output is Z. Now this is already done. Step 2. Step 2 is we make our state table. We make our state table. All right. 0, 0, 0. Right? So if you look at it, your state table, sorry, there's a mistake here in the state table. Let me correct that. This is the next or future state. This here is the flip-flop inputs, and this is the system output. All right, let's do this. So the first step, guys, the first step, I asked you to do this problem, finish off this problem. All right, the first step for the present state, the left-hand side, the present state is the present state of the flip-flops. What does the flip-flop already hold, right? And what is X? X is the system input. System input. All right? That's the system input. Okay. Now, on the left-hand side, before the double line over here, basically you have Q1, Q2, and X. They can be thought of in terms of your truth table like your input, right? You input your current states and you input into the system, which is your system input X. It can be thought of as your input into the truth table. So therefore, because there's 3, therefore there'll be 8 possible combinations. So how do you fill up that side of the table? You just go all possible combinations, 0, 0, 0, all the way till 1, 1, 1. Now, there's a second group over here. There's 4 groups. The first group is on the left-hand side, present state and system input. There's the middle group, which is the flip-flop inputs. What is the flip-flop inputs? Then there's the future state or the next state of the flip-flop. Then the system output. Can you see there's a whole bunch of them? All right. Now, the left-hand side, present state and system input, we just go and populate it like a normal truth table. 0, 0, 0, 0, 0, 1, all the way till 1, 1, 1. Everyone happy there? Okay. Now, how do we do the flip-flop input? How do we do the flip-flop input? D1. How do we get D1? Now remember, our D1, we were able to calculate the formula by looking at the circuit. Without any knowledge of sequential logic, we were able to calculate the formula for D1. From where? If you come here, can you see that's the formula for D1? How did we calculate it? By analyzing the circuit. No need for combination, sequential logic. It's all combinational here. D1, D2, and X is all combinational. All right. So D1 we deduce by this. So can you guys call out what you guys found for D1? Anyone done this problem? Yeah, can you just call it out? Is this 0, 1, 0, 1? So line 5, 1, 0, 0 is 1, 1, 0, 111 is 1 again. Anybody else? Does that look right? So D1, guys, D1 and D2 is found from the formula. Can you write that down? D1 and D2 comes from the formula. Okay? All right. Now, let's look at Z. There's something else called Z. Z also comes from the formula. I'll show you. Look over here. Can you see Z also comes from the formula? Right? Everyone happy? D1, D2, and Z. There's a formula. We are left with the last two guys. The Q1 star and Q2 star. Or you can say Qn plus 1 of 1 and Qn plus 1 of 2. Remember we used to say n plus 1, which means next state. Or n plus 1 is same as star. Alright? Okay. Everyone happy with that? So what do we do here? We go to the characteristic table. Characteristic table. For which flip-flop? So let's show you the characteristic table. Okay, we are doing the D flip-flop. Our circuit has got which flip-flop, guys? It's got the D flip-flop. So, which table are we going to use? There's two sets of tables. One is the one in the middle is what table? The characteristic table. Alright, the D flip-flop characteristic table. The one on the right is the D flip-flop excitation table. Now, which flip-flop, which table is appropriate? Both tables are related. They both belong to the D flip-flop. But they're used for different purposes. Now let's look at the characteristic table. In the characteristic table, the input into the flip-flop is given. Yeah? If you look at it, the D flip-flop has only got one input, D. The current state is given, and we want to find the next state. What about the excitation table? The current state is given, the next state is given, the desired state, next state, and on the right hand side, what do we have? It's D. D means what should be the input for you to go from Q to Q star. So we don't need the excitation table. We want the characteristic table. We have the current state, we have the current input, we want to find out what is the next state. Can you guys quickly just scribble this table in the middle down, these 4 lines, on your piece of paper? Can you scribble that down on your exercise book where we're doing the problem so that we don't need to travel back and forth? Happy? Everyone okay? Right? 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 1. Set. Just put it down on the same page where we are trying to fill up this state table. Okay. Set. Happy? Okay, I'm going to flip back now. So let's fill this up. Q1 is 0, D1 is 0. You have to match 1 to 1, eh? Okay? Q1 is 0, D1 is 0. So therefore Q1 star will be 0. Q1 is 0, D1 is 1. Q star 1, Q1 star will be 1. Look at your table. Right? 0, 1. What is it? 1, 0 gives you 1. Oh, sorry. Yeah, 1, 0 gives you 1. Right? Yeah? Everyone happy with that? Let's do the next one. Okay, Q is 0, D1 is 0, 0, 0, 0, 0, 1, 1, 1, 1, 0, 1. I'm moving to line 2 now. 0, 0, 0, 0, 0, 0, 0, 1, 0, 1. There we go. Do it yourself. I'm going to give you time. Do it yourself and populate your table yourself. Yeah? Okay. So that's our state table, guys. That's our state table. That's done. That's like in your exam, I think that was 7 or 8 or 10 marks or something like that, just to do this table. Right? You will be given a circuit and you will be required to draw the table. All right. Okay. Now, our question doesn't end there. The last part of the question is, to draw the state diagram. Keep this there, right? I'm going to move it to the side. I hope you've done it. The last part is to draw the state diagram. Okay? Now, state diagram will look like this, guys. There's two flip-flops. So, for two flip-flops, how many possible states can there be? 0, 0, 0, 1, 1, 0, and 1, 1. So, 4 bubbles. 1, 2, 3, 4. Put it in a circular way. All right? 4 bubbles. 0, 0, 0, 1, 1, 0, and 1, 1. Yeah, 4 bubbles. Okay. We have 4 bubbles. All right. Now, okay. So, do you see how I got those 4 states? Because there's 2 flip-flops. Each flip-flop stores 1 bit. So, how many possible bit combinations can there be? Right? 0, 0, 0, 1, 1, 0, and 1, 1. 4 possible bit combinations. So, those are in our bubbles. This refers to flip-flop 1. Where's our problem? Oh, yeah. The problem is on the screen, right? Flip-flop 1, flip-flop 2. Okay. So, that refers to flip-flop 1. That refers to the state of flip-flop 2. All right. Now, let's look at our state table again. You need the state table. It's just like, remember when we were doing combinational logic, you had Kano maps and you had truth table. And you also had Boolean algebra. All 3 are the same thing, just represented in different ways. So, the state diagram is the same thing as the state table, except for it's just a representation. Okay, let's look at the first line. Q1, Q2 is 0, 0. First line of your state table, right? 0, 0, X is 0, right? And what does it become? Q1 star, Q2 star remains at 0, 0. Yeah, look at line number 0, right? So, there we go, and we say X is equal to 0. And what is Z equal to? Z is equal to? Z is equal to 1. All right, now let's look at the next line. Let's go line by line. 0, 0, we come here. You have to look at your state table, guys. You need to look at your state table. 0, 0, it becomes 1, 0. X is equal to what? 1. Y is equal to, Z is equal to 1. Am I correct? Yeah? Right? Okay, now let's look at the third line. 0, 1 becomes 0, 0. X is equal to 0. Z is equal to 0. 0, 1. Let's look at the fourth line, third line, line 3, 0, 1, 2, 3. 0, 1, all right, I'm here now, guys, I'm here. 0, 1, X is 1, and it becomes 1, 0. 0, 1, sorry, 0, 1 becomes 1, 0. X is equal to 1, and Z is What is Z there, guys? That's 0. Next line. 1, 0 stays at 1, 0. 1, 0 stays at 1, 0. And the way we put it is x slash y. We say x is 0, sorry, z, x slash z. Z is 1. 1, 0 goes to 1, 1. Next line. X slash z is 1 slash 1. 1, 1 becomes 0, 0. Everyone with me over here? You see what I'm doing? 1, 1 becomes 0, 0 with x as 0. That's x slash z. And z is 0. 1, 1 remains at 1, 1. X as 1, z as 0. That's your state diagram. You have done an analysis. All right, so basically, this diagram pretty much gives you a state. So, this diagram pretty much says that, hey, if your number output is 0 and you insert the output in you input x is equal to 0, it will stay at 0. It will display 0. If you insert 1, right, if you insert x is equal to 1, your state will become number 2. It will start to show number 2. From 0, it will jump to 2. 2 is 1, 0, right? Yeah. No, this 2 is not hidden. This 2 is not done in our, no. For state diagram, you don't look at D1, D2, no more. Yeah, for state diagram, for state table, you need this. But state diagram, you just look at this line and this line. Yeah. All right, guys, a good question from my friend over here. What happens to the inputs? If you look at our state table, there was a section there. There was the input section, Q1, current state and next state, right? The Q1, Q2. There's also another section for Q1 star, Q2 star. There's a section for X, there's a section for Z, right? There's a section for D1 and D2, right? D1 and D2. Okay. D1 and D2, we don't use that. We don't use the input into our flip-flops in our state diagrams. That doesn't show up. That gets lost out, right? If somebody wants to develop that, they have to go from the state diagram. Okay? All right. Does that answer your question? Yeah. So, yeah, no, for this, you need to look at the characteristic table. Where's the characteristic table? Yeah, you need to look at that in order to fill this. Okay? Yeah. Right. Okay, guys. Let's do one more flip-flop. I just give you a background to the D flip-flop. Right, so that's one problem. Okay. Okay, we'll have a quiz now. All right. Just pass this around. Okay. More coming this way. Some more coming. Yeah, there's more coming that way. Please back. All right. All right. Some more. All right, guys. It's not a quiz. We're just going to do an in-house activity. How many? Any floating around? Any floating around? Yeah, there's some at the back over there. what I'll do is in the next lecture I'll photocopy some more. This is not a quiz. This is just a problem. So just to save us time in drawing the problem, we'll do this. Okay. All right. But this is exam. No, this is slightly weaker than exam. Slightly easier. Slightly easier. In your exam, your flip-flops will be mixed up. In your exam, your flip-flops will be mixed up. So one will be a D, the other one, the second one at the bottom. What I mean is within question 1, can you see it's both D right now? Right? Within question 1, it's both D. In your exam, one will be a D, one will be a T. Right? Okay, so it'll be mixed up, not consistent. Okay, so make sure you take note of that. All right. Let me just do a brief explanation. How many guys without the in-class exercise? Hey, is there any over there in the corner? No? Okay, all right, don't worry. On Wednesday's class, I'll photocopy some more and I'll bring it over, all right? Okay? Okay, in the meantime, I just wanted to talk, because we're using so many D flip-flops, just quickly, I wanted to give you what is a D flip-flop. And we'll come back to question number, I think we'll start off with question number 2. Question number 1 is almost like what we did just then. Okay, what is a D flip-flop, guys? A D flip-flop is basically, if you remember, I'll just give you some background into a D flip-flop. So we already know what an SR flip-flop is, right? Now, let us take this situation. So let me just show you what an SR flip-flop. Okay, remember this guy here? That's your SR flip-flop. Yeah? That's your SR flip-flop. I just want to introduce you what D is, because we've been doing some problems on D, so it's good that you know how D is made. Remember, what did we use to build our SR flip-flop? We used the SR latch. We took the SR latch, we added a clock pulse, and we added some NAND gates, and we made it into the SR flip-flop. SR flip-flop, the difference is you can now control it. You can, for every clock pulse, the state changes. Right? State changes according to the input at the clock pulse. At the clock pulse. So only when you press clock, the state changes. All right. Okay. Now, okay. We now want to build a D flip-flop. What is a D flip-flop? So from here, I hope you have this in your exercise book somewhere. This is the SR flip-flop truth table. Now, a D flip-flop is this. Okay, so that SR flip-flop, that's Q, that's Qn plus 1, or sometimes they call it Qn plus 1 is also synonymous with Q star. Oh, sorry. That's supposed to read Q bar, yeah? Sorry, yeah, that's supposed to read Q bar. Q and Q bar. Okay. All right. And we have your clock line here. Okay, so this is your SR flip-flop. This is your clock. All right, set? Happy with that? Okay. Now, how do we build the D flip-flop? Just like how we use the SR latch, we build the SR flip-flop. Now, I show you how to build the D flip-flop. All we do, guys, is, so this guy here is this guy. Right, that's just put into a box, you get that. Set? Okay, now, all we do is take that line, put a NOT gate there, there. That's your D flip-flop. Easy peasy. All right, from SR to D. And the way we write it down is same thing. We represent that. Let me draw that in black. Hey, we already drew it. That's our clock. That's our D. That's our Q. That's our Q bar. Yeah, we did the problem already. But now I'm giving you the background of how we built it. So, guys, let me just do a quick thing over here. So the SR table flip-flop, the truth table for SR look like this, right? Let's just do it very quickly. The truth table, this guy, right? I don't want to damage the notes here. So it was clock, S, R, Qn plus 1. Set. And we had, I'm just copying it from here, 0xx, 100, 101, 110, 111. And we said, hey, this is Qn, this is Qn, this is 0, this is 1, and we say, hey, this is invalid. Right? Set, so copy, I just copy paste from here to there. SR flip-flop. But hey, now, I want you to tell me, have a look at the diagram. If you have a 0 here, what will come into S? It will be 0. And what will come into R? 1. And if you have a 1 here, what will come into S? 1. And what will come into R? 0. So what happens to this truth table? Two combinations cancel off. You can never have, therefore, this line here, S and R can never be the same because there will always be opposites. Can you see? These two will always be opposites. So S and R will always be opposites. Right? So what happens? This line here cancels out, bang, and this line here, S and R is the same. Never occurs. Just never occurs. So therefore, the new D truth table, this here, truth table for D flip-flop. The new truth table for D flip-flop has only what? 3 lines. 0, 1, 1. Right? And of course, S and R are opposite, but we only have one input, and that is D. So what does it look like now? Let's draw it out. You have clock, D, Qn plus 1. Right? So what do we get? 0x, 0x, and Qn. Clock, there's only 2 possibilities, 0, 1, all right, and you have 0, 1. Just want to show you this. Okay, we only have one input now. Come back here. We only have one input. Yeah, so it's only one input. The new input is D. So let's just put a dotted line all around that. All right, can you see what's happening here now? Right? We have only one input. It can be either 0 or 1. And what's the other input? It's clock. And we have 2 outputs. So 0, 0, 1, whatever goes into S. Yeah? Whatever goes into S. Even this line here gets cancelled out. Why? Because we only have whatever's going into S. R is internal now. So we just copy that. So whatever's left of the truth table is 0xqn 1 0 0 1 1 1. There we go. That's the new truth table. Right? Okay, let's take it one step further. This is D flip-flop. All right, set. Everyone happy with that? Okay, let's now look at the D characteristic table. The DFF characteristic table. Well, same story, guys. Same story. Remember how we did the characteristic table for thing? It's the same thing. You have Qn D Qn star. And if there's two inputs, 0 0 0 1 1 0 1 1. And 0 0, if we come back to here, let's look at this corner over here. 0 0, what does it give you? Qn, which is a 0. 0 1 0 1 will give you what? Just a 1. This will give you a 1 0 will give you a 0, right? So 0 over here, that's that case there, it will always give you Qn. So that's it. Oh, sorry guys, I think that's supposed to be a 0. Sorry, yeah, that's a 1 and that's a 1. So in the end we say Qn plus 1, which is equal to Q star, is equal to D. So that's your characteristic table. That's your characteristic table. Okay? Now, what about your excitation table? D flip-flop excitation table. For excitation table you have Qn, you have Qn plus 1, and you want to find out what your input D will be. So you have 0 0 0 1 1 0 1 1. And all you got to do is read